All right, so we're going to look at a proof of the sine rule today, but I just want to share this idea that I came across recently. I think it's very relevant. So the curious paradox is that when I accept myself just as I am, then I can change. So Carl Rogers was a very famous humanistic psychologist, and that was in his book On Becoming a Person in 1961, which I thought was just interesting. I feel like it's so easy to fall into the trap of not accepting ourselves and accepting things the way they are. But that's sort of a first step if we want to change and grow. So I thought that was an interesting one. What we'll do is we'll look at a proof of the sine rule. It's actually pretty straightforward, I think, so hopefully don't have too much difficulty with this concept. First thing just to say is that we're no longer looking at things like Pythagoras, where we're looking at right-angled triangles. We're now looking at things that aren't right-angled triangles. So you can imagine any triangle that we're going to call A, B, C, this big blue triangle here. And we just give some names to things. So we'll call this the height of the triangle. This line, for your interest, is called an altitude. If you drop a line from the top down to the bottom of a triangle, it's called an altitude. You could also drop one from here to there rather. It'd also be an altitude if you rotated the triangle. And actually, I don't even think you need to rotate the triangle. It would still be considered an altitude if it went from there to there, I think. Without rotation, obviously, you can't depend on any sorts of rotations. Anyway, lowercase letters are going to represent the side lengths, so A, B, and C down here. And what we're going to do is we're going to come up with this interesting rule. So let's have a look at what that is. We're basically going to break it down into right-angled triangles. So first thing I want us to do is to look at A, C, D. So we're going to look at this right-angled triangle. Okay, and I think you would agree, if you think about your trigonometry, if you think SOHCAHTOA, sine is opposite over hypotenuse. So if we're at this triangle here and we're thinking sine of capital A, now capital A are these points, so sine of A represents the angle at this point here. It's equal to h over b. Well, h is the opposite side, b is the hypotenuse, so we've got h over b, and so sine of A is equal to h over b. Now if we rearrange that, for h, we get b sine A. So we can see that h is equal to b multiplied by sine A. Okay, so that's sort of our first part, looking at this sort of left-hand right-angled triangle here. The next one, if we look at the right-angled triangle BCD, so this one on the right, we get sine of b equals h on A. So we get that h equals a sine b. If we just rearrange that, but now we've got h equals b sine A and h equals a sine b. So therefore b sine A must equal a sine b. And so that's how we write that there. And then this, if we just divide through by sine A and divide through by sine b, we just rearrange it. Essentially these are the same line. We don't really need to rearrange it, but generally speaking, the sine rule is written in this format. And then so we get a proof of the sine rule. So it's pretty straightforward, I think. Now I'll just explain this last part. If, as I said, we were to drop an altitude from somewhere else, so for example to drop the altitude here, I think you could imagine that we would get another relationship that would say C on sine C for the exact same reasoning as we've got here. So yeah, that is a proof of the sine rule, and it has lots of interesting applications. Basically, you're going to use it in a couple of situations, and I'll just pause to tell you exactly what those situations are. Yeah, so we use it when, if you think back to all the congruency and similarity stuff you might have done on triangles, when you've got AAS, so you've got an angle, and a side, or you've got ASA, two angles and a side. And we'll talk about it in another video, what's called the ambiguous case, but you can use the sine rule when you've got SSA, so two sides and a non-included angle. But in that situation, you can end up where you've got two possible triangles that could exist, but we'll talk about that a little bit later on. So yeah, this triangle also moves because why not? Because obviously this is all talking generally. So yeah, hopefully you found that useful. That's a hopefully pretty straightforward proof of the sine rule. Good luck. We'll talk about, I've already made a video on the cosine rule and sort of proving that, so you can go check that out as well if you're interested. But we use that when we get given other kinds of information. So good luck with all your studies, keep up the good work, and I will see you soon.